And we'll talk about complements, 2's complement and all. So one of the very important note you need to keep in mind, that only 2's complement has only 2's complement form, right, has unique representation of unique representation of zeros of 0. Only 2's complement has unique representation of 0. So if I talk about sign magnitude form, okay, of 0, and 1's complement form of 0, right, and the 2's complement form of 0, right. How 0 is represented in these three formats, right? So in sign, if this is plus 0, right, so we will do like this, 0 0 0 0, okay, and but for the sign you will have to put 0 extra 0, right, and okay, this 0 will denote this is a positive one, and suppose this is minus 0, okay, so there must be 1 as a sign bit 1, and the magnitude is going to be 0 only, right. So 0 has got two representation in case of sign magnitude format, okay, remember. And in case of 1's complement, is suppose this is 0, okay, so plus 0 means what? It will have same representation as sign magnitude form, okay, so it will be 0 will be the magnitude sign, and these are the zeros in 1's complement, right. But if it is a 0 minus 0, right, so you will have to take the 1's complement of 0, right. So 1's complement of 0 will be what? 1's complement of zeros, I mean 0 0 0 plus 0, right. 1's complement of plus 0 you will have to take, so means that 0 0 0 0, right. So its complement 0 is represented like this. It will be same as sign magnitude format, so 0 0 0 0, but this 0 will be denoting the sign one. Minus 0 is there, so it will be also same, right. 2's complement of plus 0, right. So plus 0 is like same only, so 0 0 0 0, and this will be denoting yes, right. So remember, always keep in mind that they are same, okay. So in case of 2's complement, the 0 has got only unique representation, otherwise here you can see there are two possibilities for in case of 0, right. Okay, now what we will do here is suppose one of the important problem let us take here is that represent the following 2's complement number, represent the following 2's complement number, right, complement number in terms of 4 bit, in terms of 4 bit, okay, and 10 bits, 10 bits without affecting its value, right, without affecting its value, without affecting its value, its value. It is very very important, right, to understand that. So the given one is what given is, it is given that 1 1 1 1, this is a block here given, right, the set of binary digits are given, right. So what you have to do here is you have to take the 2's complement of this. So once you will take the 2's complement of this, so 0, this will be 0, this is 1, and rest are the zeros, right. And after all, the sign bit is what? Sign bit is 1 here, so this will be minus of 6, right. So 6 minus 6, okay, this binary format denotes minus 6 in the decimal equivalent, right. So now what you have to do here is you have to represent in 4 bit, okay, this binary format has to be represented in 4 bit, right. So let me take again 1 1 1 1, right, and 0 1 0, okay. Now see, 4 bits are there, right? And these are the bits which are being repeated, okay, because of sign extension. Okay, so what we have to do here is, this is basically the sign bit extension, right? Because of sign bit, so you can discard them, right? You can discard this. So if you want 4 bit only, so you can write 1010, right? And now you can take the 2's complement of this, 2's complement. Okay, so nothing is gonna change, just minus of the 2's complement of this, right? So okay, so if you are going to take the 2's complement of this, so what will be having here? So it will be 0 1 0 1. So this is 4, this is okay, 8 4 2 1, right? So here you can see in case of 4 bit, right? So this will be you can represent here bit. You have discarded what? You have discarded these 3 bits. Okay, these extra 3 bits you have discarded. You are considering only 1 0 1 0, right? So you have considered this. Now what you have to do here is you can take what? So you will be taking this, okay, 4 bit, okay, representation. And if you're going to take the 10 bits here, so 10 for 10 bit you will have to do the sign bit extension, right? So sign bit extension means what? So it will be like how many bits are there? 1 2 3 4 5 6 7, right? 1 2 3 7 bits are there. So you can go for sign extension concept, right? So 1 1 1 and 1 1 1 1 0 1 0, right? So they will be denoting the same value, that is minus 6 only, right? And this will also denote the minus 6 only, right? After discarding, right, you have to discard here. After converting, you have to discard. So if you are discarding this 1 1 1, if you are discarding this, still it will denote 6 minus 6 only, right? So remember always that you can discard the this repeated sign bits, or you can add sign bits as well, okay, to extend. So according to your requirement you can do, okay. This was very important concept. And now we will talk about the range of numbers represented using n bits in all those 3 forms, right? So the range of number, from this also question can be expected, right? Range of numbers represented using n bits, okay, in all those 3 formats. So number 1 is what? Number 1 is sign magnitude form, right? And number 2nd is one's complement form, and number 3rd is what? 2's complement form, okay. In case of one's complement form, you have to represent the range will be 2 to the power n minus 1 minus 1, right? The maximum to plus 2 to the power n minus 1 minus 1, right? So it is symmetrical here. You can see sign magnitude form will be symmetrical always, okay. And right, this is what the range from minus 2 to the power n minus 1 to plus 2 to the power n minus 1. And for one complement it will be same as the sign magnitude only, that is minus 2 to the power n minus 1 to 2 to the power n minus 1. This is maximum, this is okay. Now in case of 2's complement, you have to start with 2 to the power n minus 1, right, up to plus 2 to the power n minus 1, right? So this will start with 2 to the power minus 1 n minus 1, right? So remember always these are the range of the numbers can be represented in these 3 formats, okay. So just for the recapitulation I'm telling you, okay. So you can also take the example. Suppose in case of n bit, right, means n equal to suppose 5, okay. So what is the range of in case of 2's complement, okay. You can say that minus 2 to the power 5 minus 1 to plus 2 to the power 5 minus 1. So it will be okay to it will be 2 to the power 4 minus 1, means it will be from 16 to plus 15. Okay, so this is one of the catch point is what the 2's complement has not got the symmetrical ranges, right? And if they will ask you number of integers, right, if they will ask you in all those three power n bits are there, right, and number of integers, how many number of integers can be there, right, number of integers. So in case of sign magnitude form, okay, so you can add, right, so 2 to the power n minus 1, right, plus 2 to the power n minus 1, and for 0 also you can include 1, right, this is for 0. Okay, so here it will be 2 to the power 2 times of 2 to the power n minus 1 plus 1, right, so you can take this 2 inside, it will be 2 to the power n and minus 2 plus 1, so it will be 2 raised to power n minus 1. So this is what the number of integers in case of sign magnitude form, right? Suppose n equal to 3, so number of integer will be 2 to the power 3 minus 1 means 8 minus 1 means 7. 7 integers will be there, right? And in case of 1's complement, I mean this will be say similar for 1's complement as well, right? Number of integers. But in case of 2's complement, okay, in case of 2's complement, right, in case of 2's complement, what is going to be you have to keep in mind 2 to the power n minus 1 plus 2 to the power n minus 1 plus 1, right, this is for 0. So what you can do here is you will have to cancel this out, right? You have got here that is 2 times of 2 to the power n minus 1, this will give you 2 to the power n integers. Okay, it is very easy, right? Okay, so these are the formulation you have to keep in mind. Okay, so the question, what kind of question you can expect? The question will be like find the minimum number of bits. Okay, find the minimum number of bits required to represent, right, required to represent a is given as 32 in decimal, okay, and b is given as minus 32 in decimal, right, in 2's complement. So they are asking in 2's complement how many minimum number of bits are required to represent them. Okay, so in case of 2's complement, okay, the range is what? The range is from minus 2 to the power n minus 1 to plus 2 to the power n minus 1 minus 1, right? So the positive number is given here, right? The positive number is given, okay? So what we can do here is, this is the range you have to first click, okay? The moment you see the question, this formula should come in your mind, okay? So let you can consider here, let n equal to 6, right? 6 bits, suppose. So this can represent from what? From minus 32 to 30 plus 31, right? From minus 32 to plus 31 it can represent, okay? If n equal to 6 is there, if n equal to 7 bit is there, so this will represent from 64 to 63, okay? So in case if they are asking like this, so you can directly tell that minus 32 will be required, the minimum number of bits will be required 6 bit, okay, and in case of plus 32, right, plus 32, the minimum bit will be required what? Will be 7, okay. In case of this will be required 7 here, okay. So because maximum it can if n equal to 7 bit, then only you will get this. If n equal to 6, so you will get 31, right? So but it must be plus 32 now, so the higher the bit we have to consider always, right? right? So keep in mind this. Okay, so minimum number of bits, this is how you can find. Very easy, right? By inspection you can find this, by inspection. So this kind of question we can expect in the gate examination. This kind of question we can expect in the gate examination, right? Okay. Next is the, okay, this is how you can represent this. Okay. Let us take a new concept, or okay, we'll not solve more problem now. So you can try this. Now we will talk about overflow in sign addition, right? What is overflow basically? Overflow. Overflow in signed addition. When overflow occurs, right? So the condition we have to know, right? Overflow occurs when the result of what it occurs. You have to keep in mind the definition here. I mean the concept. It occurs when result of signed, okay, result of signed arithmetic exceeds the range of signed number representation, exceeds the range of signed number representation, okay. What is the, whatever the range is, right, it should not exceed, otherwise overflow will occur, right? This is what the important concept is. Overflow in signed addition, it occurs when the result of signed arithmetic exceeds the range of signed number representation, okay. So what is the method to find overflow in a signed okay, so just I'm going to give you the methods, right? So method, okay, what you have to do, suppose you are adding these two numbers, right, and if the result exceeds, okay, exceeds the range of signed representation, then you can say that yes, there will be what, the overflow, okay. So what you can do here is, suppose this is the concept, right? So you know, when you will add two numbers, so you will get internal carry, you can say C in, okay, and one carry will be there, that is C out, okay, after adding MSB as well, right? So this is a sign bit basically, okay, sign bit. So you have to keep in mind, if C in equal to C out, if C in will be equal to C out, no overflow. Remember, if C in equal to C out, then no overflow will be there, no overflow, right? That is, the result is within the range, that is, the result is within the range. When we will take some example, you will understand, right? And the V is what, if C in does not equal to C out, there will be overflow, right? Overflow occurs, okay, and result is exceeded the range, right? Result is exceeded, okay, the range, right? So what you can do here is, you can consider this as one XOR gate kind of a concept, right? So we will talk about gates, right? So C in and C out is there, right? So when overflow will be there, okay, it will give you the overflow, right? What is the condition for XOR? If I see A and B, right, so it will be A XOR B, right? So XOR means what? XOR means excluding the B status being 1, right? Means that if 0 0 is there, so it will be 0. If 1 1 is there, it will be 0 always. 0 1 1 0, it will respond, means 1 1, okay. This is what the condition is. You have to understand this is the truth table for XOR, right? So if both are same, okay, if both are same, no overflow, right? If C in and C out will be 0, so no overflow, okay, no overflow. If C in and C out will be 0, no overflow. But in this case 0 1 and 1 0, there will be overflow, right? So we have to take care of this. Okay, this is what the method 1 through which you can determine whether there will be overflow or not. And the method 2 which I like, okay, method 2, overflow occurs, okay, overflow occurs if two positive numbers are added, okay, if two positive numbers are added, right? Numbers are added and the result is negative. Numbers are added and result is what? Result is negative. Okay, in that case the overflow will be there. Okay, so if by looking at the question you will be able to determine, yeah, they are the positive numbers, and if you are adding, okay, if you are adding them, then what you can say, two positive numbers are added. If the result is going to be negative, then definitely okay. Or if you are adding two negative numbers, if two negative numbers are added, okay, and the result is what? And the result is positive. These are the two important conditions for the overflow, right? Remember. So from here also you can expect one question if they will give you, okay. But complements, definitely one question will be there, right? So let us take one example and then understand the overflow condition here. So consider 3-bit 2's complement numbers, right? Consider 3-bit 2's complement numbers. Okay. What is the range of numbers in case of 2's complement? 3-bit means minus 2 to the power n minus 1 2 plus 2 to the power n minus 1, right? We can say that it will be from 4 to plus 3, right? This is going to be the range. Okay, this is going to be the range. Now what we have to do here is okay, this minus 4 and plus 3, right? Minus 4 and plus 3 we have got here using 3-bit. Okay, right? Suppose we have to add 2 and 3, right? This is what the range this is how we can find the range in case of 2's complement. Now we suppose we are adding plus 2 and plus 3. These are the two positive numbers, right? We are adding, so we can convert into binary format. So this will give you 0 1 0, right? And this will give you 3 bits are there, so we have to consider 3-bit. It will give you what? It will give you 0 1 1. So in fact, by looking at the binary format as well, we can say yes, this is what the positive number only, right? Because 0 is present, so we can add them, right? So let us add them. So this will give you 1, this will give you 0, right? And here again you have got 1, right? C in is 1 here, so it will be giving you 1, right? So what you have got here is the C in is 1, right? And C out is what? C out is what? 0. See, there is no carry output carry, right? So C out is 0 and they are not equal. If they are not equal, 0 and 1 means there will be overflow. Okay, if they are not equal, see, we are adding two numbers and we are getting negative result, right? We are adding two numbers and we are getting negative result here. Okay, we are getting negative result here. So we can take the 2's complement of this. So we will get here is that 1 1 0, right? Means this is minus 3, okay, in 2's complement. So the very first method what I have told you is that you have to see in and see out, right? So seen here is seen is 1 and see out is, this is method number 1. Okay, so seen does not equal to see out. Okay, see out is basically 0, right? So overflow is occurred. Okay, and in case of method 2, directly you can claim that yes, there will be overflow, right? In method 2, what you can claim, if you are adding two numbers and you're getting negative numbers, right? You're adding two numbers, binary digits, okay, and you are getting what? The negative numbers, right? So directly you can say that when two positive numbers are added, okay, the result is negative. The result is negative, okay, right? This is what the concept is. Very, very important concept you have to keep in mind. You can consider it like a XOR, okay, and you can solve this. I hope this is clear. So many times in the test series as well, you will find questions range of the number, okay. Now let us take one of the important problem. Suppose you have to add two negative numbers, right? Consider in 2's complement form. Consider in 2's complement form. So we will add two negative numbers, right? Suppose we are adding -2 and -4. We are adding them, okay. The base is 10 only. So 2's complement form, how can we represent 2's complement form? 2 means 1 0 and there will be 1, and 4 means it will be 1 0 0, right? Okay, so this is what the 2's complement. Now what you have to add here, right? So plus 0 1, and now 1 plus 1 0, right? Means C in is 0 and C out is 1. You can see here 1 carry will be there, okay. So if C in does not equal to C out, means that what? Overflow is there. This is method 1. And in case using method 2, what you can say that if we are adding two numbers, right, and we are getting positive because the sign bit is 0 here, right? And okay, if we are adding two numbers, okay, negative numbers, right, and the result is what? You are getting result as positive, because in case of 2's complement you always neglect this C out, right? You will neglect that C out, okay. So because that is end around carry kind of concept you can think of, right? So this one you have to neglect, right? So this is negative number, okay, so sorry, positive number, right? Adding two positive, okay, adding two negative, sorry, adding two negative and you are getting positive, so there will be overflow. There will be overflow. So method 1 and method 2 both are clear, right? So overflow do not occur when positive and one negative numbers are added. This is also one of the very important concept, right? So you can write here overflow do not occur, right? Do not occur when positive and one negative numbers are added. In the examination in MSQ multiple select question they might ask. So example, if I take one example to explain you, that is +2 and -4, right? So +2 has got the representation like 0 1 0, right? 3 bit only we have to consider, and -4 means 1 0 0. Now add them, so 0 1 1. Here you can see this is what the -2 -2 10, right? You are adding one positive one negative and you are getting definitely negative, okay. So you have got -2 as well, right? This is what very easy concept, and there is no overflow. In sign subtraction overflow occurs only when both numbers are different signs, of having different signs. So this is big and important note, right, for the GATE 2020 in the signed subtraction, right? In signed subtraction, if you're subtracting two numbers, right, and so in that case overflow will be occurring. Okay, when overflow will occur? Overflow, okay, overflow occurs only when overflow occurs only when both number have different signs. When both numbers have different signs, right? In case of subtraction, in case of addition, that concept is different, right? In case of addition, I have told you, right, around method 1 and method 2. But in case of subtraction, how can you okay, how can you okay, and two numbers are subtracted, so whether they will overflow or not, so you have to keep in mind that the overflow occurs only when both number have the different signs. Both number have the different signs. Okay, different signs. This is very important concept, right? So let us take one example and subtract and see whether overflow is there or not, right? So suppose minus 6 and minus 4, they have same sign, right? So no overflow will be there. They have same sign, so no overflow will be there. It will give you minus 2 only, right? Within the limit only, so no overflow because they have same sign. Suppose you are subtracting minus 6 and plus 4, right? So it will what? It will be minus 10, right? So it is out of range. Okay, it is the magnitude, magnitude go out of range. Okay, out of range. So there is a chance for overflow. Chance for overflow. So I hope this overflow concept is clear for everyone. If you will watch lecture or you will be watching lecture in future or before 5 days now, GATE is there, right? So you might understand everything. Okay, you can revise from these lectures. I hope this is clear for everyone. Okay. Let us take you can take a look previous questions, right? And we'll talk about the advantage of 2's complement now. Advantage of 2's complements. What is the advantage of 2's complement? Why we are talking always the 2's complements, right? So basically it has unique representation as we know. Okay, and it has more number of it represents more range of the numbers, right? First of all, it represents more range of numbers, say integer, right? 2 to the power n integers. And second, only one addition is done here, right? In case of 2's complement, only one addition. Okay, when subtraction is converted to addition, when subtraction is converted to addition. Okay, these are the advantages. So they might ask you questions. I mean, they might give you the options and you have to select. Okay. And third, you can say expect is EAC need not to be remembered. Means we always discard EAC, right? EAC need not be remembered. Okay. This is also one of the very important concept. And fourth one is what it has unique representation of 0. It has unique representation of zeros. So already these things we have you know. And what are the applications of 2's complements? So 2's complements are used for arithmetic complements, right? And 1's complements are used for logical complements, right? Just like self complementary code and all, we will use 1's complement. So application you must know, right? So basically 2's complement application is in the arithmetic complements, arithmetic, complements. And 1's complement application is what? 1's complement has got application in case of logical complements such as self complementary code and all, when we will discuss logical complements, right? Complements. So hopefully everything is clear till here. Okay. Yes. So application advantage, these things you have to keep in mind. Okay, now we will talk about binary codes. Now we will talk about binary codes. So binary codes are basically we will see two kind of a code. One is alphanumeric codes, right? Alphanumeric codes, right? And second one is numeric code, right? Numeric only. Numeric code. Alphanumeric codes. Okay, in case of alphanumeric code, they are further of two kind. We will see that one is very popular, that is ASCII code, right? ASCII code. Okay, and second one is EBCDIC, right? EBCDIC. Okay, so ASCII code, basically you don't have to study in much depth about this because it is not that important, but you must know how many bits are required to represent ASCII code. 7 bits. Okay, so 2 to the power 7 means 128 alphanumeric. Okay, alpha you have to keep in mind, 128 total. And this will be EVCDIC will be using 8 bit, right? 8 bits are required to represent this, means that 2 to the power 8, 256. Okay, so these two information you have to keep in mind. And in case of numeric codes, we'll see a binary coded decimal kind of a code, right? VCD and all, right? So in case of numeric codes, this is in our syllabus, right? So we will talk about binary coded decimal, right? BCD, right? Binary coded decimal. Okay, binary coded decimal you have to keep in mind. And binary coded decimal will be of two kind. One will be weighted VCD and one will be non-weighted VCD, right? So this classification also you have to further classification you must know. The weighted VCD and non-weighted VCD here. Non-weighted VCD. In non-weighted VCD, you will study about gray code. Okay, gray code is non-weighted gray code, and this is very important in case of digital communication as well. Gray code, and in case of K map. Okay, in K map we always go for gray coding, right? According to the adjacency rule. Okay, access 3 code. Here we will talk about access 3 code. So gray code, access 3 code, they are non-weighted VCD, right? And 2 out of 5 code, right? 2 out of 5 code. These are the codes which we use always in case of error detection, right? In communication system, right? And gray code is also known as, it has got different name, unit distance code, because each successive bit will differ by 1. Okay, each successive code will differ by 1, so that is known as gray code, means unit digit will be there. You might be familiar with Hamming distance. So between two codes there will be only one bit differing, right? So that is what the property of gray code, unit. So in error detection and all, it will be very easy. Unit distance. Okay, and access 3, it is sequential and self complementary code. Okay, access 3 codes are sequential and self complementary, right? Sequential and self complementary. So these are important properties which we are talking about, right? And weighted VCD means what? Natural VCD code, you can say directly, natural VCD codes, right? Natural VCD codes are what? 8421. Natural VCD means 8421, right? Codes. And self complementary codes are what? Okay, you have to keep this in mind. Self complementary codes. Self complementary means just like 2421. Okay. Okay, what are the codes which can be said that they are the self complementary code? The sum of okay, sum should be 9, always keep in mind. Sum of weight, okay, should be 9. Then you can say that yes, sum of weight should be 9. Then you can say they are the self complementary codes. Yeah, 2421, 3321, right? 631 minus 1, right? And 84 minus 2 minus 1, 5421. These are the codes, right? They are the weighted code, and they are also known as I mean these. If you will add them, the sum of weight should be 9, right? So this will not be the self complementary, because 5 plus 4 9, it is exceeding 9, right? But these, okay, will be the self complementary codes. This, let me highlight here, this, okay, will be the self complement, but this and this will not be the self complement. Okay, right? So self complementary codes, self complementary codes. So if you are good at basics, so your digital communication, your K map concept, everything will be easier, right, to understand, because you are familiar with gray coding, you are familiar with these binary codes and all, so nothing will be tougher. And if you're not good at basics, then there is a problem. Always there is a problem, right? Okay, so what is self complementary code? Complementary codes. So in these codes, the code of a digit, right? Remember, the code of a digit, right? The code of a digit and the code of nines complement of a digits. Code of nines complement to each other. It is the property of self complementary, right? The code of a code of a digit and the code of nines complement of a digit, right, are the complement to each other. So this is the statement we have to see. And self complementary codes are used in VCD subtraction, right, used in VCD subtraction, right. They will ask question, yes, self complementary codes are used in VCD subtraction. These things you have to keep in mind. Okay. Right. So 6, 3, 1, -1, they are the self complementary codes. Okay. Okay. Right. So we will take more problems. Okay. And we will talk about VCD addition, VCD subtraction, accessory codes and everything, right, in the next session. Right. And we will also see the code conversion, how to convert from binary to gray. Okay. And we'll realize the using basic gates, right, and we'll realize them as well. Gray to binary, right? Binary to gray and gray to binary. Okay, so these are the logical arithmetics we need to understand. Directly we can't we can't define, we have to understand, right. Definition is not enough. Okay, anything, if I'm going to write any statement, we need to also realize that. Okay, so the moment you will realize, you will understand. So gray to that, okay, gray to binary and binary to gray, these are the two important conversion. And two